So in this series of videos, I want to discuss the RL and RC step response, sometimes called force response. For this particular lecture, I've taken the slides from the Electric Circuits textbook by Nielsen. I believe that book presents a very clear explanation, and so I really like the videos that they use here. They're a little bit more complete. So before we get into the lecture, a couple of reminders. First, when we work with inductors, we're always solving for the current in the inductor, the transient current in the inductor. And the reason is it's the inductor current that can't change instantaneously. So this means that across t equals 0, if a condition changes, like a switch opens or closes, we know that in the instant before the switch closed and in the instant after the switch closed, the one thing that must remain constant across that is the inductor current. So that gives us then an initial condition. When we work with capacitors, we're solving for the transient voltage in the capacitor because it is the capacitor voltage that can't change instantaneously. And the other thing to remember from the graph that was shown for the RL and RC natural response circuits is that after 3 to 5 time constants, the stored energy in the inductors and capacitors is fully dissipated, and all of the transient effects are over. So somewhere between 3 to 5 time constants, just depending on your application, you can, for all practical purposes, assume that you have a DC circuit, meaning the inductors look like short circuits and the capacitors look like open circuits. Now this has consequences, because what this means is if you have a circuit that's been connected and sitting for a long time, quote unquote, you can approximate the circuit to look like DC. So in the words of textbook authors, a long time means more than 3 to 5 time constants. All right, so let's just get started then, and I want to illustrate first of all what we would refer to as a step response of a first order RL circuit. So once again, by way of review, it's referred to as first order because it has a single energy storage element, one inductor. It's called a step response because we have a source here. And when we have a source, this is a DC source. And notice that we have a switch that closes at t equals 0. So this has been sitting. The inductor obviously would have no current because there's nothing providing any energy to the inductor. It's been sitting, and then suddenly at t equals 0, the switch closes. So it's called a step response because if we were to look, basically the voltage source in the circuit looks like nothing until the switch closes, and then suddenly we have that voltage source that is turned on and becomes an active part of the circuit. So this kind of function where you're equal to 0 for t less than 0 and you're equal to a constant for t greater than 0 is referred to as a step function u of t. And this is defined in this chapter in your textbook. It's not essential to define it here, but it is a concept to begin talking about because we use it quite a lot in circuits too. So what we're going to do is we realize everything had 0 initial conditions before the switch was closed. So when we close the switch, initially the current through the inductor is 0 because it was 0 when the switch was open. And so just thinking through this logistically, what will happen is immediately this voltage will have to appear across this resistor, meaning that we will begin to draw some current. So it can't all appear across the resistor. In fact, in the instant the switch is closed, it all appears across the inductor. Then as the current is allowed to build up, the voltage will appear mostly across the resistor. Then as time goes on, the inductor begins to look like a total short, and the current then will just be like what the current would be at infinity if the inductor were short-circuited. So let's go through and look at the mathematics because I think that might be a little bit easier to understand. So we close the switch and then we write a mesh equation or a KVL equation around this loop with the switch closed. So if everything were on the same side of the equal sign, we would have minus Vs plus I times R plus L di dt. Moving the source voltage over to the opposite side of the equal sign, we end up with this equation. Now we're going to follow our same approach. First we want to isolate the dI/dt part. So we move it over to the other side of the equal sign. We do some algebraic manipulation, and then we do some more algebraic manipulation. And then remember what it is we want to do is we want to separate the variables. So we want all of I on one side of the equation, and we want all of t on the other side of the equation. So we basically take this term in the parentheses and we move it over to the left-hand side. Erase my mark here. So we move this term in the parentheses to the left-hand side, and then we move the other term to the right-hand side. So at this point, no differential equations, really not even any calculus. We've just done some algebra so that we can get all of the i's on one side and all of the t's on the other. We then do exactly what we did in the previous section on the natural response. We're going to integrate both sides. So we integrate the left side from the initial condition on the current to I of t, letting dx be a dummy variable, which as you note in previous lectures, I'm not really much of one to use dummy variables, but it's not a problem if you do. It's just a way to distinguish that our upper limit will be I of t. So we can substitute that dx and then plug in the limits. But you don't have to do that. If you can keep your i's together and make sense out of that, that's not super essential. Then on the right-hand side, once again, the substitution of a dummy variable. In my lecture, I just left this dt and integrated that, and that's perfectly fine. But it's fine to do it this way as well. Just depends on what your mathematical comfort level is. Then taking the integral of the left-hand and the right-hand sides and substituting the limits and using the property of the natural log, that the difference natural log of a minus natural log of b is natural log of a over b. We do the integral here and a little bit of algebraic manipulation, and we end up with this expression. Now we want the natural log to go away because we don't want I to be inside of a function. So we take e and raise it to both sides of the equation. So when we do that, the natural log, e to the natural log of x is equal to x. So on the left-hand side, we get this expression for I of t, and on the right-hand side, we get a function of time. And then solving for I of t, which is actually what we want, we end up with this expression. Okay, where V of s is our source voltage. So let's go back. That's our source voltage. And once again, if we let time go to infinity, this inductor looks like a short, and the current through that inductor as t goes to infinity is going to approach via the source divided by the resistance. So that's what this I sub f means. That's the final value on the current. I sub 0 is the initial value on the current. This is the final value on the current. This is the general form of an equation for the step response of an RL circuit. Tau is the time constant. You can see that if we took this R over L and rearranged it so that it was in the denominator, tau is L over R. So we've got the time constant, we've got the final value of the current, we've got the initial value of the current. So now let me say that when you work one of these problems, you now have the general form for what happens in one of these problems. So you have to, in an RL circuit that is forced, or that is a step response, you have to find three things. You have to find the initial current, I sub 0. You have to find the final current. What's the current going to be when the time approaches infinity? And you have to find the time constant. Once you find those three things, you can plug into this general equation. So summarizing kind of a recipe for a method, and this is one of the reasons I like the Nielsen book, because he does a lot of this sort of listing recipe. Stepwise, the first thing you have to do is you have to determine what is the initial inductor current I sub 0. You can only do that if you analyze the circuit for times less than 0. So you're going to have to do your first approach for what happened before any switches move for t less than 0. the next thing you have to do is you have to calculate your time constant, L over R, and you're going to do that for the circuit when t is greater than 0. So after any switches have moved, anything has happened, you have to find L over R. R is basically the equivalent resistance that is seen by the inductor. So if you think, for example, in terms of Thevenin equivalent resistance, it would be the Thevenin equivalent resistance seen at the inductor terminals. And then finally, we want to find the final value of the current as we let time go to infinity. Once we have those three things, we can plug into the equation and have the solution immediately. And then at that point, once you've solved for the inductor current, then if the problem is asking for other things, you can solve for those other things. But if, for example, the problem is asking for the voltage across a resistor somewhere and you have an inductor in there with a switch and an initial charge and a DC voltage source, you can't solve for anything else until you solve for the inductor current. So that is something to really keep in mind. A lot of people will start off trying to solve for various unknowns in the circuit. You can't do any of that until you solve for the inductor current. The reason for that is the inductor current is the only thing that's going to stay steady across the opening or closing of a switch. Okay, so here's an example problem that will hopefully put some methodology behind some of the stuff that we've been talking about. So mostly we'll focus on finding this expression I of t. That's defined as the inductor current here, which once again is the only thing we can solve for initially in a circuit like this. We can't solve for anything else until we find the inductor current. Then we want to find the initial voltage across the inductor right after the switch moves, answer some questions about whether or not that makes sense. And then we want to look at how many milliseconds after the switch is moved does the inductor voltage equal 24 volts. Okay, so we're going to analyze this to find the things that were previously mentioned in our little recipe, and we're going to do this step by step. So the first thing we want to look at is we want to look at before the switch moves. So we're sitting here in position A. So this entire sort of left-hand side of the circuit is not there. We just have the right-hand side of the circuit. It's hooked up. And then at t equals 0, it's going to move to position B, meaning for t greater than 0, all the stuff on the right hand of the inductor is going to go away. So let's take it one step at a time. The first thing we want to do is we want to look at the circuit when the switch is in position A. So let's go back. So the switch is over here. It's been sitting for a long time. The inductor looks like a short. And remember, the current in the inductor is defined from top to bottom node here. Okay, so there's where my inductor was. Okay, here is the circuit for t less than 0. The inductor looks like a short because it's been sitting for a long time and the transient effects are gone. Because this is a short, when this 8 amps divides, nothing will go through the resistor, and 8 amps will go through the short in the bottom to top direction. So because of the direction in which I sub 0 was originally sketched in the circuit, we need to basically stay with that. So I naught is equal to minus 8 amps. So that's your initial condition on the current in the inductor. Okay, the next thing we want to do is we now want to look at what happens when the switch moves. But this is not at infinity. This is just after the switch moves. So the switch is moved to position B, and now what we're interested in is in finding the time constant. Now, in finding the time constant, what you basically need to do is you're looking really at finding a Thevenin equivalent. But unless there are some dependent sources in the problem, which we're not actually going to deal with this semester because you actually don't see that very often in RL and RC circuits, in circuits without op amps. So we're not going to look too much at that. So basically what you need to do is you need to find the Thevenin resistance or the equivalent resistance as seen by the inductor. So locate the inductor, and then looking into those terminals, what is the resistance that's seen? And remember, to find an equivalent resistance, you have to kill the sources, which in the voltage source means we short it. So basically the equivalent resistance seen by the inductor is 2 ohms. So our time constant tau if you recall, is L over R. So we take L over R and we end up with 0.1 seconds. Okay, so now we're 2/3 of the way there. We found the initial condition on the inductor current and we found the time constant. So if you recall from the little recipe, the thing that we need to find next is we need to find the final current. So now the final current means as t goes to infinity. So once t is infinity, remember the transient effects have died away, because what was our time constant? 0.1 second? Yeah, our time constant was 0.1 seconds. So 3 to 5 time constants is half a second. So after half a second, the inductor no longer looks like an inductor because the circuit looks DC again. So now once again, the inductor appears to be a short. And so that's how we're going to calculate the current as t goes to infinity. That's a simple Ohm's law. 24 volts divided by 2 ohms is going to give us 12 amps. So the final current, 12 amps. So now we just take our formula for the inductor current and we plug in for each thing. We plug in for final current, we plug in for initial current, we plug in for tau. And once we do that, we get this expression here at the bottom. And now notice here that we specify that this is for t greater than or equal to 0, because that is true. Because if we take t less than 0, we had a different circuit. So these are called transient circuits. These effects happen because you threw a switch and some energy has to reshuffle, charge and or discharge inductors and or capacitors. And so you have these short-lived transient effects, usually characterized by exponential functions with a given time constant. Notice this is written as minus 10t instead of t over 0.1, and that's fine. Notice if we let t go to infinity, this term goes to 0 and we end up with 12 amps. Notice when t is equal to 0, this becomes minus 8. So our solution is consistent with what our initial and final conditions were in the circuit. Okay, the next thing was to find the time at which the inductor voltage equals 24 volts by solving the following expression. So let's go back, because I think maybe I got this out of order. Let me see here real quick if maybe I flipped no, guess not. I guess I just left that out. So if we come back and we wanted to find the voltage across the inductor, how would we do that? We would use our equation that says the inductor voltage is what? Do you remember? It is L di dt. So the derivative of I with respect to t, the first term would give us 0, the second term would give us 30 e to the minus 10t. The inductor value gets plugged in, and so you get an expression then for what the inductor voltage looks like. Now, we want to know when that equals 24 volts, so we substitute in 24. We have our expression for the inductor voltage, and then we basically solve for t by dividing 24 by 40, taking the natural log of both sides, and then getting rid of the 1/10. And if you do that, you find out that that time is 51 milliseconds. So once again, this is not, this particular question, it's not really a question that I would give necessarily on an exam, but this one is. So here we have a plot of current and voltage as a function of time. So you can see, and really I want to talk about the current. We start off with our initial condition of minus 8 amps, and you can see we approach 12 amps. So this is the same kind of exponentially shaped curve. Let's draw a dashed line. So you may remember when talking about the natural response, we always had exponential decay, and I mentioned that for every time constant you expect to be at 0.368 where you were before. So if you look at this as a beginning point and this as an ending point, you're like 63 1/3% of the way there at one time constant, and then you're another 0.6 0.68 after the next time constant. So you're going from your beginning point to your ending point as defined by your exponential time constant, which means that after 3 to 5 time constants, you have, for all practical purposes, approached a constant here at 12 amps. All right, we can do a similar derivation for the RC circuit, and I won't go into quite as much detail. Basically, here we have a capacitor that was sitting with no charge. This is drawn as a Norton equivalent, a current source in parallel with the resistor, so that we can actually make this a single node circuit and we can write a node voltage equation. The reason to write a node voltage equation is so that we can put things in terms of the capacitor voltage, which is what we always want to solve for in an RC circuit. We always want to solve for the capacitor voltage. And then we can always find the current later. So we take we write a node equation here, which is given up here at the top, or KCL, whatever you'd like to call it. Do some rearranging and some more rearranging. You can basically see that this equation has exactly the same types of terms that the RL circuit had. The only thing different is we have C and RC instead of L and RL. So if you follow exactly the same solution mechanism, you actually end up with exactly the same equation, where you have a final condition on the voltage, an initial condition on the voltage, and a time constant. Which means that for a circuit involving an RC, we first determine the initial capacitor voltage, analyzing the circuit for t less than 0. We then calculate the time constant, looking at the circuit for t greater than 0. We then calculate the final value for the capacitor voltage by letting time go to infinity and the circuit become DC again. We then use our equation and plug in our values for the final, the initial, and the time constant, and then and only then do we calculate anything else that we're interested in learning about the circuit. So here's an example on determining the step response of an RC circuit. So in this case, we had a switch that was in position 1 for a very long time. And then at t equals 0, it moves to position 2. And so what we would like to find is we would like to find the voltage across the capacitor as a function of time. And then we'd like to find the current across the capacitor as a function of time. However, notice the difference here. Here we say t greater than or equal to 0. For the current in the capacitor, we say t greater than or equal to 0 plus. The reason for that is that in a capacitor, the current is allowed to jump instantaneously from one value to another, because the physics says the capacitor voltage has to stay constant across a switch. So in order for both KCL and KVL to be satisfied in the circuit, as well as the law of physics about the capacitor voltage cannot being able to change instantaneously, the capacitor current has to be allowed to do an instantaneous jump. So I believe you'll see that illustrated in this problem. All right, so initially we analyzed the circuit for t less than 0. So looking back at our original circuit, that means the switch is here at position 1. The entire right side of the circuit is not connected to the capacitor. So we only have these elements. And for t less than 0, this capacitor looks like an open circuit. So that's what's illustrated here. My capacitor would be between these two terminals. You can see that when we pull all that out and we replace the capacitor with an open, we have a simple voltage divider here. And so we can find the initial condition on the capacitor voltage. It's going to be 30 volts. Alrighty. So now what we want to do is we want to find the equivalent resistance as seen by the capacitor. So they kind of do some weird and unnecessary stuff, I think. You don't really have to find a Norton circuit. What you can do is you can say we want the equivalent resistance here. Looking into these two terminals, we can replace, to find the equivalent resistance, we can replace the voltage source with a short. When we replace the voltage source with a short, we have 40 in parallel with 160. And then when we calculate that, we get 32. And then we have that in series with 8. So we find the parallel equivalent here, which is 32. We put that in series with 8. We end up with 40 kiloohms. No problem with what they've done here. It's just, in my opinion, this step is not necessary if you don't have any dependent sources. In fact, they say short the 75 volt source, make series and parallel combinations. And here's that Thevenin resistance right here. Okay, now what we want to do, I guess the one thing that this does make easy is when you let time go to infinity, then it's pretty easy to calculate what the voltage across the capacitor will be. So that would be the one advantage of that. All right, so now what we need to do is we need to let t go to infinity, which means the capacitor once again looks like an open. So we would have, oh, I'm sorry, before we do that, let's figure out what the time constant is. So we found that our Thevenin equivalent was 10 kiloohms. Our capacitor is 0.25 microfarads, so we take our RC and we calculate tau, which ends up being 10 milliseconds. Okay, now we're ready to calculate the final voltage. So the final voltage, we replace that capacitor with an open circuit. Now they've done this with the Thevenin, or the Norton, that they already calculated. You could just as easily have done it with a Thevenin, where the entire Thevenin voltage would appear across the terminals. Let's go back and look at that circuit. Here's the circuit. Let's do some erasing. So let's erase my short. And if t has gone to infinity, and basically this capacitor is gone, it's an open. And so now you can see the output voltage is a simple voltage divider. It's going to be the voltage across the 160K resistor. So in fact, you could find the open circuit voltage, you could find the Thevenin equivalent, and then that would give you the voltage across that capacitor. To be honest, I'm totally not sure why they went to the trouble of calculating the Norton. And to also be honest, I've actually never done this from a Thevenin perspective. It's actually pretty clever. I've just always, when I was ready to let t go to infinity, calculated this voltage at the terminals. But since it is the Thevenin voltage, if you find the Thevenin equivalent, that's a pretty clever way to go. So we now have our final voltage. So we now have our initial voltage, we have our time constant, we have our final voltage, and we're ready to plug in. So when we plug in, that's what we get right there. So here is our equation. Now I is C dV dt. So if we want to get the capacitor current, we basically will take dV dt here, multiply by C, and this is what we get. Okay, now let's talk just a little bit about what happened with the capacitor current. Initially, for t less than 0, the capacitor was an open circuit and we had no current through the capacitor. Now, as soon as the switch moves, the current's going to jump from 0 down to minus 2.25 as soon as we've moved the switch. So for t greater than or equal to what we refer to as 0 plus, the instant that the switch moved. So this expression is valid for t greater than or equal to 0 plus, and what happened was the current jumped. So I had, get a different color here. I had 0 current, and then it jumps down here to minus 2.5, and then exponentially approaches what? What happens to the current eventually? Well, eventually that capacitor looks like a short. As t goes to infinity, this approaches 0, so the current's going to approach 0. But there is this instantaneous jump in the current, which has to happen in order for both KCL and KVL and the laws on capacitor voltage to be maintained. Okay, so one interesting thing is you noticed that the RL and RC circuit had a very similar form. And so if we replace the inductor current and or the capacitor voltage with just this variable X, we can write a general solution or a general equation. Now, something kind of interesting is this actually also holds for the natural response. So in a natural response, you may remember that there's no forcing function, but you do still have an initial condition. In a natural response, because there's no source, the final condition on capacitor voltage and inductor current is that they're going to go to zero. So you can use this for the natural response if you let your final value become zero, as it does. So really this one formula can be applied to everything that we've discussed on transient circuits so far. The only thing is, okay, X is current for an inductor and it is voltage for a capacitor. And as long as you follow that rule, then this formula can be applied if you just have DC sources, a single capacitor and a Thevenin equivalent resistance, then this can be applied to any situation. So if you want to use the general method, you identify which variable you're solving for. As we said, it's the inductor current for RL. It's the capacitor voltage for RC. You find the initial value, analyzing the circuit for t less than 0 right before the switch closes. You find the time constant, which is L over R for RL circuits and RC for RC circuits, where R is the equivalent resistance that is seen from the terminals of the inductor and or capacitor. You then calculate the final value by letting time run to infinity, replacing capacitors with opens and inductors with shorts. For the natural response, you realize that the final value goes to 0. And then you can write the equation for x of t by plugging in each of the unknown quantities for t greater than or equal to 0. So this equation applies for t greater than or equal to 0. Obviously, as t goes to infinity, this term is going to go away. The circuit approaches DC, and your x of t approaches whatever the final value is. At that point, once you've got this equation, you can then work with this equation to get any other quantities that were of use or interest in the circuit. So that concludes what I want to discuss about the step response of RL and RC first order circuits, and also an illustration of this general method that works for both natural response and step response.